Hello everyone. So it's my pleasure to welcome you to this new appointment of our under 40 lecture series. So we start after a small pause, and today it's my pleasure to have as invited speaker Dr. Giancarlo Sorrentino. He's a researcher at l'Istituto di Scienze e Tecnologie per l'Energia e la Mobilità Sostenibile, STEMS, so in National Council of Research in Italy. Previously, he was assistant professor of chemical plants at the University Federico II of Naples, Istituto Ricerche sulla Combustione at CNR in Naples from 2015 to 2017. Now, Giancarlo has a wide range of research interest, in particular, low pollutant emissions and high efficiency combustion modes like mild combustion, with an emphasis on CFD modeling and experimental characterization of this oxidation process. He's the secretary of the Italian section of the Combustion Institute. He's the vice chair of the CIFER construction and also a member of the ILAS Europe Board Committee. Giancarlo is the author of several publications in international journals, and today we'll talk about mild combustion, so the physical and chemical mechanisms that control this combustion regime, and so he will discuss how we can improve and move towards a better understanding of this very promising combustion regime. Thank you very much, Giancarlo, for having accepted our invitation, and I give you the floor for your presentation.
Thank you. Thank you, Alessandro. Can you hear me? Yes, I think so.
Yeah, very well.
We'll try to share the presentation. Can you see my screen?
Yes.
Okay, thank you. So thanks a lot again for inviting me to this webinar. I want to thank also the Belgian section of the Combustion Institute, all the organizer of this very interesting and fruitful webinar for all the combustion community. I have to admit that I was 40 when I accepted this invitation, but I became more or less 1 week ago 41, but I think that this is not an issue. So today, as Alessandro said, I would like to point out some aspects related to mild combustion and some physical and chemical mechanisms, especially when related to their interaction for the modeling of this peculiar combustion regime. So just a few words on the institute, on the National Research Council, where I am a permanent researcher. Consiglio Nazionale di Ricerche is mainly organized in several departments, and in particular, our institute is belonging to the Engineering, ICT, Energy and Transportation department, and in particular, the STEMS Institute, that is it is mainly related to science and technology for sustainable energy and mobility sectors. Its headquarters is in Napoli, in the city of Naples, and the research at STEMS is mainly organized in different key areas. In particular, I want to underline some that are more related to the topics that I will talk today, especially the decarbonization and energy transition, and also in some ways to the digital transition in the energy and transportation sectors. Of course, there are more than 100 scientific staff, some technicians, administrative, and plenty of PhD students and master students. So when related to the talk of today, our group is a part of our group is related to the research interest is related to mild combustion, and from an experimental point of view, we have different facilities. In particular, related to the study of kinetics of this combustion regime and the interaction with the turbulence and heat transfer in lab scale reactors. And we're working by following this scale bridging approach that I will also underline later, where we can start from very simple and zero-dimensional characteristics of the combustion towards semi-industrial and industrial application of this regime. Of course, we also perform CFD simulation to design apparatus and to validate experimental results, along with chemical diagnostics, modeling, and optimization for the kinetic schemes. Our team that is we call Pyrolysis and Mild Combustion Lab is mainly composed by 7 plus me, 8 researchers at different levels, as I said before, we are mainly focused on combustion processes, sustainable combustion processes, and the pyrolysis processes for mainly for biomass. There are also some PhDs and postdoc that works in our lab and that are framed in different research projects that are mainly based on the same topics. So, in order to introduce the topic of today, I want to underline that one of the main driver of the energy transition that is related to several sectors is especially guided from the emission of CO2 that is relevant for especially for hard-to-abate sectors. As we can see from here, we have different EV industries and energy-intensive sectors that are very difficult to decarbonize, and in particular, this is a key point, especially for combustion engineers. In particular, in this framework, the International Energy Agency identified several scenarios to decrease this kind of CO2 emission, and in particular, the main drivers were related to the efficiency of system, renewable, and also to these fuel switching methodologies where we can that can help in particular to reduce greenhouse gas emissions. So it's very important to frame this kind of scenario related to the CO2 emission reduction, to the variability of this future energy mix that require flexible, efficient, and clean combustion technologies. And in particular, it's very important to address, in order to address the previous challenges, it's very important to have combustion technologies that can be framed in this kind of scenario. So one of the possible solution could be mild combustion that respond to this kind of challenges. In particular, this kind of combustion regime, I will talk about timescales later. But if we see to the system temperature with respect to a conventional combustion regime, it is framed in a lower temperature regime with respect to conventional combustion systems. And if we want to define mild combustion as the one of the most accepted definition in the literature, is a combustion process where we have that the maximum allowable temperature increase is lower than the mixture auto-ignition temperature, and the initial temperature of the fresh reactants is higher than the mixture auto-ignition one. This is very important to underline that this kind of conditions this kind of condition need to be obtained can be obtained also at the local scale of the combustor. So it's not necessary to have external preheating and external dilution of the fresh reactants, but through the if we tailor properly the aerodynamics of the systems and we design in a proper way our combustion system, we can obtain locally also this kind of condition. Of course, we're passing from something that is like a flame, so where we have a localized heat release on a flame surface, to a system where we have a volumetric heat release on the whole combustion chamber. And this can occur since we are operating in a very diluted combustion, in very diluted conditions, so very close or outside the flammability limits, and in very preheated conditions where mixed or auto-ignition is happening. So we have a sort of paradigm shift where we are passing from a flame stabilized process to a change, and we have a change in the perspective in the analysis of a combustion problem, from a purely energetic to something that is very close to a chemical reactor. So if we see to the definition of mild combustion in this kind of regime, in this kind of diagram, where we report the initial temperature with respect to the oxygen content, we can identify 4 main areas. In particular, if we are below the preheating of the fresh reactants is too low, we are below the ignition temperature, and the dilution of the system is too high. So we are at very low oxygen concentration, and the temperature increase is low. We cannot stabilize the combustion process. On the other hand, if we are inside the flammability limits, so the oxygen concentration is higher, and we are reactants that are not diluted, we have a standard combustion process that are ones that we have studied on the combustion book. So is a combustion process that is mainly stabilized through a feedback of the heat released by the flame toward the fresh reactants. So locally, I have this. We have this kind of feedback mechanisms from the flame toward the reactants that are preheated. If we think to the classical thermal theory for a premix flame, we have this kind of reactants that are preheated up to the ignition temperature, and this is a local process, of course, that is obtained on the micro scale. On the other hand, if we are at preheating temperature higher than the ignition one, we are in the high temperature combustion regime. And finally, if we have in a condition where we can stabilize the reactive process through preheating to the preheating of the fresh reactants at temperature higher than the ignition one, and to dilution levels higher than the conditions related to a standard combustion mode, so outside the flammability limits, we can obtain the mild combustion regime. So if we are able to stabilize this kind of combustion process, we are passing from a condition that is very similar to a flame condition to something that in literature is called flameless, since it's related to the invisible feature of the reacting process. So we have different, very peculiar characteristics that are used for several applications, such as the uniform temperature and species distribution inside the reactor, the volumetric combustion. So we have a volumetric distribution of heat flux, of scalars, of also the heat release. We have a noiseless process and close to net zero of pollutants emission. This can be realized, as I said before, through external or internal recirculation. And in particular, we have a strong effect of the turbulent intensity and of the kinetic time scales. How can we realize usually this kind of a solution from a technological point of view? Well, as I said before, if we base this on inlet condition, we can realize this through external dilutional preheating, but this is not a necessary condition. In particular, we can realize this kind of condition also at local scale. For example, by acting on the aerodynamics configuration to create locally highly preheated and diluted conditions. So we need to locally preheat fresh mixture to temperature higher than the autoignition one and simultaneously dilute it by rapid mixing between hot products and reactants. At the same time, we need to create large strain to leave flame for very good premix, and this means if we think to a diffusion flame to have a very high strain rate. So this can be obtained in several ways by tailoring, let's say, the boundary conditions of our process. And we can act on the aerodynamics, on the material properties, on the geometry, on the heat exchange through the surroundings. We will see some example in the following slides. So as I said before, if we think to a conventional flame, so to the standard Maillard-Chatelier theory, for a premix flame in a propagating structure, we usually have that outside the flammability limits, if we dilute with the combustion products the fresh reactants, we are not able outside the flammability limits to stabilize a flame. This is not true if the process relies on autoignition, since it can be also stabilized for non-flammable mixtures. So as I said before, this kind of process is, from an industrial point of view, from a technological point of view, stabilized by means of Barnett gas recirculation. Usually we have this KV parameter that is the recirculation ratio, that is a ratio between the exhaust mass flow rate and the inlet mass flow rate that is used as a parameter for industrial application to monitor the occurrence and to, let's say, have an idea of the occurrence of flameless combustion. Some more basic studies based on DNS also pointed out how this flame structure is changed in an homogeneous heat released on the wall reactor when we are passing from a flame type to a flameless or a mild combustion zone. In this case, we usually have that the Dunkeler number is lowered, and this is mainly due to a dramatic change in the kinetic time scale. And we have also some effect on the fluid dynamic and time scale and on the heat loss and radiative reabsorption. So the stabilization procedures make the numerical modeling very challenging, in particular in terms of kinetics, turbulent chemistry interaction, and heat transfer. And today I would like to point out the main challenges related especially to the interaction between the turbulent time scale and chemistry, and how can we study how the reactive structure is different with respect to the flame type. So for sure we need detailed chemistry to model this kind of process, and later I will show you some examples. So if we move into chemical kinetics, we have I just reported some studies, some previous studies from our group. We have that in particular where we have highly diluted reactants. We have highly diluted reactants and preheated. We have we can alter strongly the relative weight of the main oxidation and recombination pathways when mild combustion occur. And in order to give more further information on this aspect, we have that under diluted and highly preheated condition, the structure of the reactive region is significantly changed. In particular, we have a very modest temperature increase due mainly to the highly dilution level. And we have this shift from kinetic regimes lower with respect to traditional system. And we are operating in a continuously autoignition conditions. So under diluted and highly preheated, the characteristics kinetic time scale change with respect to the ones that are involved in traditional systems. And in particular, if we think that we usually obtain this process to great amount of CO2 and water that are recirculated, we have strong effects of strong kinetic effects of water and CO2 from a thermal and kinetic point of view on the process. So if we see at the structure of the reactive region, we have that for conventional flame we have this deflagrative of diffusive interface that are mainly obtained through the heat that comes from the flame. So the structure of the flame is mainly related to the heat released by the flame. On the other hand, if we study if we see in the literature the structure of a mild reactive region, we have this kind of structure mainly related to autoignition kernels that are transported by convection mechanisms and grow in time and space. So they give an appearance of a uniform process, mainly at the micro scales, but we will see that usually we can have different behaviors at the micro scales with respect to the macro one. There is a pioneering work by Plessing and Peters where they show this kind of the transition of this kind of behavior in a burner for a furnace when passing from a premix methane flame to a flameless oxidation. And we have this shift in the behavior from a surface stabilized, let's say a temperature, a discontinuity in the temperature along a steep along an interface for a flame condition, and on the opposite we have this smooth transition of the temperature when passing from burned to unburned condition. The same is obtained for the OH, for example, and we will see more later on this specific aspect. So the main physical feature from an application and technological application point of view, we have the absence of visible flame, uniformity of temperature and species distribution, low noise, especially this is very important for thermoacoustic application. And in fact, this kind of regime is also related to other kind of names in the literature of this combustion process, such as flameless, noiseless, or colorless. When and mainly this kind of name are related not to the specific condition that we realize inside the combustion chamber, but mainly to the fissure, let's say to the outlet fissures of the the combustion process. So it's mainly related to the specific application of this regime. So this kind of features are very important for a variety of application, especially the uniformity of the temperature for hard-to-abate industries and also the high radiativity transfer, but also the fact that we are operating in a continuous continuously auto-ignition processes. This permits to oxidize and to stabilize the combustion process also with, for example, low-grade fuels with very low heating value. So we have a large fuel flexibility of the combustion process, especially when compared with a conventional one. Just some notes on the application. This kind of technology is used in furnaces, especially in the steel industry, but also in ceramic and in chemical one. And some other application, but they are specific to at low TRL levels. There are also some kind of commercialized system but they are very few. They're used also for microgas turbine for combined heat and power, and also there are a lot of applications for boilers, for example. So on the basis of what we have said up to now, it's important to underline that despite the application of such concept to EV industries, the development of mild combustion in other fields, especially through a CFD-guided design, is hindered by previous issues. So specifically the decrease of kinetic rates leads to low Dunkeller number that usually in literature are reported that are close to unity. So it's of paramount importance to introduce detailed chemistry for the optimization of the design in this kind of combustor, and thus chemistry plays a crucial role due to the relevance of finite rate. In particular, where we are moving from high to low temperature regime, the chemical activity tends to decrease as the main effect related to the reactants dilutions. So the chemical time scales are slower with respect to standard combustion case. We can see this from this very simple diagram. So if we are in high temperature combustion regime, we have that turbulence chemistry interaction are limited since their overlapping on time scales between mixing and turbulence and chemistry are very limited. So usually what combustion engineers do is to use very simple chemistry modeling, such as the one related to reduced chemistry or simplified chemistry, also 4 or 5 step reactions to model this kind of combustors, or for example by relating on the flamelet, on the simple flamelet, steady flamelet approach, and results are very good usually. This is the main reason is why we have this limited overlap between the flow and the chemistry time scale. So if we go to low temperature combustion regime, as we said before, chemical time scales are longer, and so we have a strong overlap between time scales. So we have an enhanced interaction between turbulence and chemistry, and it's very important to account for such interaction with detailed chemistry modeling. So usually researchers do that in different kind of lab scale apparatus. There are several literature papers, especially on jet flames, where this kind of phenomena are represented, but they are not taken into account in a comprehensive way, since for example in jet in optical flow flames we are not dealing with the Wall effects or the effect of the recirculation and heat transfer on the combustion process. This can be done. So this kind of modeling and the previous issues can be also addressed in different kind of lab scale apparatus that were built in the past for studying this kind of process. We have mainly two kind of classification based on the aerodynamics. So we can have reverse flow and also swirled or cyclonic flow combustors. In particular, this kind of confined environments permits to study also the effect of vitiation and wall heat transfer at the walls on the ignition and on the oxidation process, taking into account also the effect of turbulence. So it's a complication, of course, of the problem, since jet flame configuration only deals on the effect of transport mainly, and on the turbulence, and their interaction with the chemistry, without taking into account other kind of effects. So if we start from what we know from turbulent combustion, and we think to the Borghi diagram for premise combustion, we can see that if we want to try to understand what happens on this kind of representation by when we dilute a reactants, when we dilute fresh reactants, of course we are changing the let's say the reaction thickness, and so in a certain way also the laminar burning velocity. So we are passing, for example, if we operate in this kind of condition in the thin reaction zone with moderate Karlovitz and Dunkohler number, if we are moving towards diluted condition, for example, we are moving in this direction, so toward what the people call distributed reaction zone. But this is mainly defined for premix combustion. So if we do the same for the Williams representation of turbulent combustion for non-premix, so in the Dunkohler-Reynolds diagram, we obtain that when we dilute, when we are moving toward a low temperature combustion regime, we are longering mainly the chemical time scale. So we are passing from a flamelet to a distributed reaction zone. So we can say that mainly the main effect of dilution on this kind of structures are the transition toward this kind of distributed ignition with very large Karlovitz and very small Dunkohler number. But this kind of regime are mainly unexplored in the combustion community. If we see some insights from the TNF workshop target flame, we can see that there is a lot of work on the high Dunkohler number flames. But when we reduce this kind of this dimensionless number and we increase the Karlovitz number toward the stirred reactor regime, we have very few experiments and very few information. So on the basis of that, if we try to see what in experiments during the year have changed this kind of dimensionless number, we can see that after 2010, mainly we had an explosion of this Karlovitz numbers bubble toward the very high Karlovitz number, especially for premix flame. And this is the same for the Dunkohler number. So we had a crisis for the Dunkohler number, where several experiments moved toward this regime. So we can say that on the basis of the application that are moving toward low temperature combustion processes and diluted regime, there are a lot of experiments in the literature that are investigating such conditions. But the question is how this kind of reactive regime can exist. If we think to what we have said before, and we refer to some literature studies, we have that mainly the increase of the flame robustness is due to the dilution of Barnett gas. So we have a reactive region that we can only stabilize if we have a significant local preheating and vitiation of fresh gases. So this is what I've said before. We don't have a propagation. Mainly, we have some autoigniting kernels that are formed and that convect downstream and growth. So we usually have this kind of distributed ignition reaction zones that is very difficult to monitor since it's very fair and with patchy appearance, and it is distributed on the whole volume. So if we come back to the boarding diagram, the question is, can we distinguish? Can we say that can we think to a corresponding boarding diagram for the scenario that I presented up to now? I think that we don't have possibility to correlate the two things. So the Bourgui diagram was taught for a combustion process that is mainly related to a propagating structure with a feedback mechanism. So since we are not in the same condition, we have a paradigm shift. I think that we cannot rely on that. And in particular, we have other different behaviors that are related to this kind of a combustion process. In particular, if we think to the classical S-shaped structure of the shaped curve of the flames in diffusion, in counterflow diffusion conditions, we have that under mild combustion, we have this dissolution of an extinction strain rate. So we have this monotonic behavior in this kind of condition. So this is a signature of the fact that we have a reactive structure that is profoundly different with respect to the previous one. This is also reported in the literature as globally distributed reaction zones when we are moving toward very low oxygen contents. If we see to some DNS studies from the Minamotes Svaminathan, so Cambridge University, we have that locally there is a broadened we can have broadened flamelets, but also distributed reaction. So these kind of behaviors are occurring simultaneously in the reaction field. So the typical question of this kind of structure are mainly related to the inception of mild combustion, to the fact that flame or ignition is predominant, and if in some part of the reactive regime we have autoignition and flame propagation that can occur simultaneously. So the morphological and topological features of the reaction zones are very important, and there is a very important question in the mild combustion community: if this kind of structure are distributed or not on all the scales, all the spatial scales of a combustor, or they can change as a function of the scale that I'm considering. Of course, the choice of a correct modeling paradigm for this kind of modeling of a combustion regime is very important, and also the kind of experimental diagnostics that we have to use. So this kind of question are very important in the mild combustion community, and more of them are still unsolved. So in order to understand what happened when I'm moving toward mild combustion, we can start from studying, since mild combustion is relies on spontaneous ignition processes, we can start from what we usually study in the combustion book. So spontaneous, the equation from for some spontaneous ignition processes, especially if I consider the one related to the enthalpy and to the chemical species. So we have the term, the accumulation term, the generational consumption one, and the one related to the convective of diffusion transport. So we can have, as a function of the dimensionality of the problem, a different elementary process that can occur. So I can pass from simple autoignition processes to diffusion ignition ones. For example, if I consider also a diffusion term. So I don't want to treat all this kind of process, but it's very important to underline that under 0D or one-dimensional conditions, a lot of literature studies were reported for all for all of these studies. I want to during this webinar, I want to underline some literature works that we have done in the diffusion ignition process. So if we think to the elementary process that can occur when we use premixed reactants or non-premixed one, we can obtain peculiar characteristics of the reactive region if we dilute and preheat. If we starting from a premixed reactant or from a non-premixed one, we dilute and preheat the reactants. So, for example, if I referring to a counterflow diffusion flame with methane and nitrogen, for example, versus air, in the temperature mixture fraction space, we usually have this kind of behavior with the maximum temperature around the stoichiometric point. If we dilute the fuel, for example, at by reaching a mole fraction of the methane of 0.1 with nitrogen, we have a different behavior of we have a transformation, let's say, of the thermochemical state space that the system can access. So in this case, of course, I have to preheat. In this case, I preheated the air to sustain the combustion process. But as you can see from here, we have changed by diluting the methane and by preheating the air, we have changed the temperature increase of the maximum temperature increase that occurs close to the stoichiometric point. And we have changed a lot also the stoichiometric mixture fraction. So we can see that by diluting and preheating this is one of the possible configuration. We have a profound modification of the thermochemical state space. We can see the same effect by if we dilute the oxidizer, for example. And if we study this kind of process in a counterflow diffusion flame, by diluting the fuel, for example, and by preheating the oxidizer, we have this kind of behavior. So if we start from undiluted condition of the fuel, so I have just methane without nitrogen in the fuel, and I have preheated air, we have that the temperature profile is the following. We have the heat release profile with an oxidation region and a pyrolytic one. So the stoichiometric point is usually located close to the maximum temperature of the system. If we dilute, we have this kind of behavior. We have that the heat release is shifted toward the higher mixture fraction, and it is also widened. If we calculate the standard deviation of this profile by approximating it with the Gaussian profile. This is an approach used by Peters. And we calculate the standard deviation of this profile. We have that it increases by increasing the fuel dilution level. So, but when we increase the dilution, we have that this kind of standard deviation is increased up to a critical point, a turning point, we can say. That's where the paralytic region is disappeared. And in this case, we can have the occurrence of this flameless behavior where we don't have a paralytic region. So where, by increasing the dilution, in this case to level higher than, to mole fraction of methane lower than 10%, we have this abrupt change in the standard deviation. So we have this steep increase in the standard deviation, and we have also another important, other two important behaviors. We have that the reactive region is broadened and it releases shifted towards the hot side. As we can see from here, the stoichiometric point should move toward the higher value, but we have that the reactive structure is stabilized at lower mixture fraction. In particular, it is moved toward the hot side. So we have this uncorrelation between the maximum heat release and the stoichiometric point. And we have this behavior that can be pointed out by this red curve, where the distance between the maximum mixture fraction, the ratio between the maximum mixture fraction and the stoichiometric one is changed with the fuel dilution. And if we compute also the Dunkoller number, we have that around 90% of dilution, we have this steep decrease in the Dunkoller number to value close to 1. So all these characteristics recall the needs for a new definition of a new process that in literature we call dot diluted diffusion ignition, in order to underline that it's very different. The elementary structures that are stabilized are very different with respect to a flame type diffusion flame, but it's mainly in this case we have a process that is mainly related to a diffusion ignition, diffusion ignition due to hot and diluted reactants. So if we study this process also in the unsteady, in a steady condition, we have similar results. In particular, in this case, we have that the process starts around the ignition starts around the most reactive mixture fraction. It is completed at the stoichiometric point. So we have a diffusive structure growth with longer ignition stabilization times with respect to a conventional flame. This kind of structures were also recognized in the literature, and we can also obtain them if we deal with premixed condition of fuel and air. So if we use fuel and air versus hot products, and we are outside the flammability limits, we have this change in the heat release profile from let's say a localized heat release to a more broadened and distributed one, and we can obtain the similar findings that we obtained before. This kind of behavior were also recognized in different experimental apparatus. I don't want to stress more on this, but it's very important that this kind of structures were also recognized in several experimental and also DNS studies by different groups. So we have a process that is homogeneous or not as a function of the length scale that we are considering, and the local structure can be schematized not as a deflagration or flame diffusion, but as a ignition diffusion process with the autoignition kernel and the ignition diffusion structures that are formed and growth in time and space. So a simple question is, if we want to model this kind of process, can we directly apply this kind of the paradigm that we usually use in the literature for turbulent combustion to mild combustion? Also, in this case, the answer is, in my opinion, is no. Since we have an ignition process that is very different, and usually in the literature, what people have done is to consider two kinds of options. So the first one is the more simple one. So to proper tune or modify the modeling paradigms to distributed combustion conditions. And some groups also found if there is a representative canonical reactor for such conditions, in order to identify new combustion paradigm, new modeling paradigm. So if we see two turbulent combustion models that are usually used for CFD, as a function of the flow and chemistry complexity, we can say in the literature maybe that mainly that the more used one are mainly two kind of modeling paradigms. So the one based on tabulated chemistry, such as FGM or other kind of approaches, or the one based on reactor-based approaches, such as eddy dissipation concept, or new approaches such as partially stirred reactor. Other ones are sometimes used, but they're related to specific, mainly to specific application. So the first option is to use a trial and error approach, where I can tune the model with respect to the results that I found in experiments. This was done in several studies, especially in the jetty not co-flow flame in Adelaide. In particular, they used the flamelet approach. So this very simple model, the steady flamelet, to represent the combustion zone. And if you see, the results were very, as a strong disagreement with the experiments with the steady flamelet. The group of Matthias Simme also tried to modify this kind of approach to tune it with respect to the experimental results. And this kind of approach gave reasonable results. The same was done by several groups, by Parente in the past, also in the group in Delft University, and in particular by modifying the eddy dissipation concept constants. They found good agreement between the modeling and the experiments. Finally, we have done also some modification in our group with respect to the FGM method, and the same also has been done by Reichardt. When this kind of tabulation methods were used, by in this case changing the models with respect to the findings obtained by the experiments. So this kind of trial and error approach gave some results, but a second option is to understand, on the basis of the findings that I reported before, there is new paradigms that we can use to model this kind of reactor, of combustion processes. Of course, simple question can be, if there is a canonical reactor for these conditions, it has to satisfy a lot of requirements. So we need to take into account flame interaction, autoignition, distributed reaction zone, ternary mixing, and also the combustion needs to be sustained for very high scalar dissipation rate. So we are moving toward to opposite modeling paradigm. So the flamelets one, where I have a model based on the gradients effects, and the other one that is the perfectly separate reactors that assumes homogeneously mixed within a local structure. So From experimental and DNS study, we had some evidences that it's not an easy task to identify this kind of new paradigm for this kind of distributed reaction region. But there are some examples. For example, the group of ULB found on the basis of DNS, tried to implement a partially steered reactor model to represent the mild reactive region, as results were very good. But there is, in my opinion, also a third option. So we can combine the two options that we said before in order to take into account the different characteristics. And this was done also in the literature. For example, there is a collaborative work between Cambridge and Kaus, where they used tabulated chemistry combined with PSR, and the results were very good. The same by the group of Fabian Maus, where tabulated chemistry were used with diluted homogeneous reactor in a furnace. And other recent approaches used the combination of tabulated chemistry with different scalar mixing model. And results also in this case were very good. So, of course, this kind of model were validated at for lab scale on jet flames reactor. Another possible question is, there is a dependence of this validation approach also on the sides and on the scale that we are considering. Of course, the question is yes, because the size and the scale is very important in especially for combustion. So since we are validating this kind of approaches for starting from flames where we have a lot of data, I think that's the new steps in this kind of research should be to validate models on to provide new information in what we would call scale bridge reactor that provide information from the lab scale toward the reactor toward the real application, by increasing in a systematic way the complexity of the system. Of course, we will have less precise data, but that can be used to validate processes that are more close to real applications. In my view, we have to find a way to validate the model by following this kind of validation hierarchy, by moving from systems that are very close to a lab scale, for example, for kinetics or for transport and turbulence, and by identifying scale bridge reactors that can couple all these kind of processes, where we can increase the complexity, but we have less data, and data that are, of course, for example, limited to certain conditions. This is very important because we are, in this way, close to applications, and we need to do both through experiments and model that cross-validates each other. In order to show some example of this kind of scale bridge reactors, I report some results that we obtained in Naples on this laboratory unit cyclonic burner, LUCI, that is mainly a mild burner based on a cyclonic flow where we have two antisymmetric inlets of fuel and air. And we can obtain for a wide palette of fuel from hydrocarbons to ammonia to alcohols and hydrogen, distributed mild combustion conditions with stable reactive region and zero pollutants. So in this case, we obtain very good results, as I said before, with the wide palette of energy carriers without any modification to the burner. So we were also able to burn pure ammonia in a wide range of operative conditions with very low pollutant emissions. These are just to show you some results. And with this kind of reactor, of course, we try to validate the models that I told before. So we had very encouraging results by using tabulated chemistry such as FGM and that were modified properly in order to account mild combustion condition, and also partially stirred reactor model. And agreement with the experimental results were good. The same was done also for ammonia, and results also in this case were encouraging. When we tried to use the same modeling approach, for example, to validate hydrogen experimental data, we found that for both the model we had some disagreements, some important disagreement with respect to the numerical results. So for example, if we see the heat release distribution, this is obtained with the partially stirred reactor. When passing from ammonia to hydrogen, we can see that we are moving the heat release. We are changing the heat release distribution in the reactors, but when the fuel is changed, and therefore we have a different distribution of chemical and fluid dynamic time scale in the reactor. And this is very important to underline that on the basis of the fuel, of course, we can have a signature, an a priori signature of the occurrence and on time scale evolution of mild combustion in our burner by comparing, for example, the chemical and mixing time scale. So coming back to hydrogen, further modeling developments were related. This is a work in collaboration with Enea, with larger dissimulation of hydrogen air in mild combustion, and we saw that by using a proper larger dissimulation environment, we are able to catch the experimental results with respect to runs. So for hydrogen, the mixing, the modeling of the mixing and of the fluid dynamics is very important, especially for this kind of burner. Just few words on the further modeling developments in this kind of scenario. So there is a very nice work of in collaboration between ULB and Cambridge Group, when they used machine learning to understand the filter density function in mild combustion and to catch information on the distribution of in this case it was for the progress variable distribution. So this kind of tools provided very important information, since usually for example, for turbulent combustion with tabulated chemistry, Gaussian and bimodal distribution are usually used, but in this case, they found that this kind of distribution were not able to reproduce the results. Another important application of machine learning to this kind of modeling approach were related to filtered reaction rate that was developed and obtained for the partially stirred reactor approach, where both premix and non-premix conditions were identified on the basis of the training data from combustion DNS. Another example of this kind of application are related to the the application of a large eddy simulation of a flameless furnace, where the group of Pascal Domingo and Luc Verviche used neural network-driven chemistry to speed up the time integration of chemistry. So this is just to underline that this kind of artificial intelligence guided tools are very important also to guide the modeling. But of course, we have to rely on it's very important always to rely on the physics. Finally, there is also a work on the ULB group that is very important for the application of unsupervised clustering for reactor network chemical reactor network generation for CFD. And this is, in my opinion, very important for the construction of digital twins for industrial applications. Finally, I want just to underline that based on the tabulated chemistry that I mentioned before, some groups also pointed out the extension possibility to extend this kind of approach by introducing dilution and heat loss controlling variable with respect to the thermochemical state, and this can increase the accuracy of the model, of course, at a cost that is related to the computational time that we need to obtain the lookup table. Same was done by our group and by a collaboration between Fiorina, Giquel, Mathiassim, and Lamoureux, where they showed also that in this case results were very good when dilution and heat loss are taken into account in the construction of the manifold. So to conclude this kind of lecture, I just want to summarize some key points that, in my opinion, are very important. So mild combustion is an important enabler for the utilization of renewable energy carriers and in the framework of the energy transition. It requires, of course, a paradigm shift, especially when we want to model this kind of systems. New reactive structure and modeling paradigms are needed for mild turbulent combustion, and we need more skill bridging experiments to fill the gap between laboratory and semi-industrial or industrial scales systems. Machine learning can be a very good tool to help this process in developing new models and to understand some, let's say, unsolved features from the simulation. Some bonus track. Mild combustion can be also used for. We have a project on that. For example, for fuel reforming. So. As a possibility to obtain fuels through the reforming in mild conditions, and also there are some application. We have an accepted paper at the symposium on the application of plasma-assisted combustion to the mild condition with ammonia, for example. So with this, I want to acknowledge. I want to acknowledge again our group, all the researchers that gave a contribution to this kind of webinar and the results that I showed, and of course also to Professor Antonio Cavaliere that provided us very important insights and very fruitful discussions for this kind of findings that I showed. I want to acknowledge also all the projects that are involved in this kind of work, And I want to thank again you for the attention and the Belgian section of the Combustion Institute for giving me the opportunity to show this kind of results and to have this webinar. Thank you.
Thank you. Thanks a lot, Giancarlo, for this quite extensive overview of mild combustion.
Too much, maybe. Sorry.
No, it's fine. It's fine. There is a lot. There was a lot to talk about, and a lot, still a lot to discover, to explore. Okay, Professor Valente to leave, so I will lead the Q&A session. So if anyone from the audience has a question for Giancarlo, please feel free to raise your hand and ask. Okay, we have already raised hand from Matteo. So please, Matteo, if you...
Hi, Giancarlo, can you hear me?
Yeah, I can hear you.
Thank you for the very nice overview. So you showed that mild has been object of research for like 20 years now, no? Yes. And there are data from a lot of heterogeneous sources. So experiments, let's say experiments on more advanced system, detailed experiments on less advanced system, DNS data. Like, do you think it is necessary or like nice if we find a way to blend data from various heterogeneous sources to like enhance models or to make the current state of the models like more reliable in this sense?
Yeah, this is a, thank you, Matteo. This is a very important question, I think. My idea is that, of course, models are models. So we need to validate models, as I said before, on different kind of scale. But if we have data from different kind of scale with different levels of fidelity, of course, the uncertainty and also the fidelity level of the data are very important. I think that this is very important for if we want to have if we want to have models that can be used for digital twins, for example. In this case, you can use data from a semi-industrial furnace, from a lab scale burner, from a scale bridge, let's say, with different level of fidelity, and you can validate models that you are aiming to use to provide quick response. In this case, I think that this is very helpful. In other case, if I want a proper model to be used, for example, in LS environments, to model specific characteristics of the mild process that occurs locally, maybe this is not the best way, I think. So it depends on the level of complexity that you want to treat.
It's important to isolate every piece. So kinetics, turbulence, and go scale by scale.
Yeah, I think that this, I mean, it is my idea that this is a useful way to do that.
Well, thank you very much.
Okay, thank you, Matteo, for the question. We have a question from the chat from Salvatore Nardi. It says, thank you, Giancarlo, for this very detailed overview. So many info. I generally appreciated it. I'll have a lot of questions, but for time reason, I'll pick just one. When you showed the effect of fuel dilution of standard deviation of T and T versus mixture fraction, you highlighted the increase of standard deviation as well as a shift of temperature peaks toward leaner and leaner mixture. I might have missed some point, but why would temperature peaks shift away from stoichiometric conditions? Could you please comment a little bit more on this?
I told this during the presentation. I shared again my screen.
Yeah, we can see it.
Okay. When we change the dilution, I'm also moving the stoichiometric mixture fraction. So this is the main reason why we are changing the temperature peak position. I answered to your question or not, Salvatore? This was the question? Or?
No, not really. Giancarlo. Yeah, sorry, I wrote this beforehand and I just copied it, and now I didn't know I could talk. So no, if you just go a little bit farther, I saw that at a certain point you see the temperature peak going, yeah, like now we
going
have
back,
the
going back, you mean?
Yeah, basically shifting on the left compared to the mixture, to the stoichiometric mixture fraction. So I was basically wondering, why would you have a temperature peak away from a stoichiometric condition?
Yeah, this is a peculiar characteristics of this diffusion ignition process. I mean, you can recognize that this process is happening when you see that temperature and heat release are moving in the opposite direction with respect to the stoichiometric point. And this is mainly happening because your reactive structure is no more related to the heat release by the flame. So is related no more to the stoichiometric mixture fraction, but is dependent on the heat release toward the hot side. Okay, so is related to the high temperature of the oxidizer. So this is the dominant process in this case. So we have no more a process that depends on the heat release by the stoichiometric point, but the reaction process is moved toward the hot part, that is the hot oxidizer. Okay, that gives you the, let's say, the enthalpy to sustain the diffusion ignition process. I don't know if I was clear.
No, definitely. Yeah, it does make sense to me. Yeah, thanks a lot.
Oh, thank you.
Thank you. Are there any more questions for Giancarlo? If not, I have one question. I guess all these peculiar feature of a mild combustion will, I mean, you show results for the fuel, which was mostly methane. I guess these peculiar feature, are there fuel dependent? We will change if we use hydrogen or ammonia or another type of fuel, or will more or less they will change, but not so much.
This is a very good question, Salvatore. Thank you. I'm not sure with that, but we found very similar features for ignition diffusion processes also with ammonia and hydrogen. Of course, what changes is not the reactive structures, but the boundary conditions. So for example, the mole fraction at which the process starts. Okay, so if we have ammonia, for example, you can reach mild combustion for less diluted, this kind of ignition diffusion process for less diluted conditions. If you have hydrogen, it's more difficult. We found that it's more difficult to stabilize in this ignition diffusion process. So you need more dilution, for example, to obtain the same behavior. So yes, the structure of the process does not change. What is changing is the condition at which you obtain the behavior. Okay.
Thank you. We have a question from Lorenzo Giuntini. Please feel free to ask.
You are muted, Lorenzo.
Hello, ciao Giancarlo.
Ciao, Lorenzo.
Can you hear me? So I have a question a bit connected with the one of Salvatore. So, like when we have hydrogen, it's I think, as you said, much difficult to achieve diluted, like mild combustion in general, or diluted combustion conditions, let's say. But in general, what is done also, let's say, when we want to dilute the reacting region, it's also, let's say, to dilute the air, the oxidizer. Okay, like if you don't have the possibility to have an internal recirculation, you can, let's say, do an external one. And what is generally done is to dilute the oxidizer with, let's say, combustion products or so on. But what about diluting instead of the oxidizer, the fuel? For example, like diluting directly, for example, the hydrogen. What do you think can happen?
No, I think
in this
I
case?
think it's better. I think it's better to dilute the fuel than the oxidizer if you want to for technological application. Of course, in some I've not showed the results, but in our cases, we haven't found any issues also with hydrogen to stabilize mild in the cyclonic. But maybe it's because we have a very strong internal dilution. So we have this kind of condition. But yes, if you don't have the possibility to dilute internally, an option for sure could be to dilute the fuel. I think it's important to longer the chemical time scale. So one solution could be to dilute the fuel, of course.
Because I mean, for example, there are many syngas that basically can contain a bit of hydrogen, but then since for example, there are lots of also inert species, and so for example, for syngas in general, there is not an issue. For example, the high temperature, the local high temperature, and so on. So I mean, instead of, because in many works we see that people dilute the air, the oxidizer, but I mean, why not diluting directly the fuel?
I agree with you. If you have the possibilities, maybe it's easier to dilute the fuel. Of course, it's not easy in several cases. It depends on the application, but yes, maybe as an impact on the process, it is more impactful, let's say, to dilute the fuel than the oxidizer, because it's not easy to decide how should be the dilution level of the oxidizer to reach mild combustion.
Okay. Thank you.
Thank you.
Okay, thanks a lot. I think there are no more questions for you, Giancarlo. So I would like to
thanks
thank
a
you
lot again
for this.
Thanks a lot again for
very nice talk about mild combustion.
Thank you.
And
thank you. Thanks
it was
a lot
a pleasure
again.
to have you.
Thanks a lot to all. It was a pleasure, and sorry if I was late.
It's okay.
Bye bye.
Thank you everyone for joining. Bye. Have a nice weekend.
Bye bye.
See you. Bye bye.